are now on the applications of first order differential equation. So there are different application for first order differential equations, but we will focus on the problems involving a certain growth or a decay on a certain substance or a certain object. And from there, so we'll be able to apply some principles of the first order differential equation, so in solving such problems. So at the end of this presentation, so we should be able to apply solutions of first order differential equations in growth and decay applications. So there are different problems that we could solve, so using the principles of differential equations, and those problems are related to the growth and the decay. So example of growth, like for example, if we want to determine the growth of the certain population over a period of time, so as long as we know the initial population at a reference time, and then we'll try to have another set of data pertaining to the population at another period of time. So once we have multiple data, so we'll be able to predict so what would be the future population, so depending on how the population increases or decreases. So that's an example of a growth. Another example would be the spread of a virus. So if at the initial stage, so these are the amount, or these are the number of people so which are affected by this virus, and then if there are no intervention that will be implemented, so what will be or how many people would be affected by that virus, so can be predicted, so using the problems involving differential equations. So for the decay, there are certain substances or certain substances that decay over a period of time. So example of which would be the carbon-14, so which is present on living creatures that which usually decays over a period of time. Like for example, if an archaeologist found a certain fossil and then wants to determine the age of that fossil, so since the half-life of the carbon-14 is known, so we could use this information so for us to determine the age of that fossil by taking how much of the original carbon-14 has decayed, and then from there, so we'll be able to predict, or we'll be able to know so what would be the age of that fossils. So those are some of the examples so pertaining to growth and the decay, so which involves a certain principle on the different methods of first order differential equation. So particularly, so most of the time, so the growth and decay so can be solved using separable equations. So and how to solve that? So let's try to define a certain growth or a decay. So if the growth and the decay is, or the rate of the growth and decay of a certain population is directly proportional to the amount present. So if our assumption is that the growth and decay of a certain population is directly proportional to the amount present at any instant of time, so therefore we have this given equation. The differential equation would be the dx all over dt. So that is the change on the amount of the substance that is present over a period of time. So is equals to the proportionality constant k, so multiplied it with k. So wherein k is the amount of substance at any period of time. So since we have the differential equation, so we could resolve this one so using separable equation. So in such a way that we could multiply everything by dt all over x, so which would yield to dx over dt, and that would be equal to multiplying dt over x, so that would yield to dx over dt, or dx over x, and that will be equal to k dt. And then if we are going to integrate both sides, so that will give us the integral of dx over x to be ln x, and then that would be equal to kt plus c. And then applying the properties or exponentiating both sides. So that would give us e raised to ln x is equals to e raised to kt plus c, and thus x would be equal to c e kt. So we're in x is the amount of the substance at any instant of time, and then c would be our constant or the arbitrary constant c, and then e raised to kt. So we're in k is the proportionality constant, and t so will be our time. So there are different methods in solving the growth and decay. So what we will be employing is we have to read carefully the given problem, and then we have to identify our given. So mostly, so those given are the initial values, or so what would be the amount of substances at a certain period of time. So we have to take a look, or we have to enumerate all the givens based from our problem. And then from there, so we have to identify as well, so whether the relation is still the same. Like for example, if the rate of change on the amount of the substance is directly proportional to the amount of the substance at any instant of time. So unless otherwise that relation is specified, so therefore there should be another relation for us to derive the given differential equation or the solution for that differential equation. So once we're able to identify the given, so we have to formulate our formula. So typically, so for growth and decay problem, so that is x is equals to CEKT. Unless otherwise, the one that I have mentioned before, that if on the given problem, it was specifically stated that the amount of change on a substance over a period of time is not directly proportional to the amount of the substance at any instant of time. So if that is the case, so we have to take a look at the relation, and then from there, so we have to develop our equation. But if the relation is just the typical relation, so that is the change on the amount of substance over time is equal to the amount of the substance at any instant of time. Therefore, we could right away use this formula that x is equals to c EKT. And lastly, so once we have formulated our given equation, so we just have to solve. So solve the differential equation, and then afterwards, so once we all have the needed values, so we are just going to substitute. Okay, so for us to better understand the problem so about growth and decay, so let's have a specific example about it. So let's solve example number 1. So it states that if a town's population doubles in 10 years, so how many years would it take for the population to quadruple? So given that the town's population so doubles in 10 years, so how many years would it take for the population to quadruple? So in this particular example, so we have to identify first, so what are the given? So initially, when time is 0, okay, so when time is 0, so let's say the population, so let me write P to be equal to the town's population. So that would be the town's population at any instant. So let P to be the town's population at any instant. So from here, so initially, So when time is 0, so what would be the population? So on the given problem, it was not specifically mentioned. So what is the population? So we could not write 0 as our start. Okay, so because we cannot produce or the population would not increase if we're going to start it at 0. So but since it was not specified, so I'm just going to use a variable. So we're in P sub 0, so that is the initial population. So at time 0, the population is P of 0. However, on the given problem, it states that if a town's population doubles in 10 years, so that means after 10 years from our reference or from our initial time, so that is P of 10. So what happens to the population? So it doubles. So if originally the population is P of 0, so after 10 years, so it doubles, so making it to P of 0. So our required then, okay, so our required then is we are to determine, so how many years would it take, okay, so for the population to quadruple. So our required then, so would be, so how many years? So to make our population 4 times the original. Okay, so in short, so we are finding the time. So how many years? So to resolve this one, so let's have our solution. Okay, so to resolve this one, so since it was not mentioned, so how the population increases, so we are assuming that the relation would be exponential. So as the derived formula that we have for growth and decay, so if it is not specifically mentioned, so what would be the relation? So we are assuming that the relation or that the growth of a certain population is exponential. So in that case, so since P is the one that we are using, so our formula then so would be P is equals to C E raised to KT. Okay, so that is our formula. Now the population at any instant of time is equals to C E raised to KT. So from here, let's try to get first, because there are a lot of variables here. Okay, so we have the P, C, K, and T. So let's apply our first given here. That is when T is equals to 0, P is equals to P sub 0. So in here, so P would be P sub 0 is equals to C, E, K, and then T is 0. And then, so from here, so K times 0 is 0. So E raised to 0, so that would be 1. So leaving us to have C to be equal to P sub 0. And then from there, so we could substitute C. Okay, so from our original equation, so that would make it P to be equal to P sub 0, then E KT. So this time around, so we were able to find the value of C. So from here, so using our initial value, that is when time is equals to 0. So usually, that is the way on how to get the value of the arbitrary constant. That is to use the relation when time is equals to 0. So now that we have a new equation, so let's use the second relation here. So that is after 10 years, right? So after 10 years, so when T is equals to 10, so the population doubles. So the population would be 2 times P sub 0. So using our new formula, so that is P which is this time, so that would be 2p sub 0, then is equals to p sub 0 e raised to k, and then our t would be 10. And since p of 0 is on the left hand side as well as on the right hand side of our equation, so we could cancel that out. So giving us 2 is equals to e raised to 10k. And we need to find what's the value of k. So to find the value of k, so we will be employing the logarithm. So ln 2 then would be equal to ln e raised to 10k. So giving us ln 2 to be equal to 10k. And thus giving us k to be equivalent to ln 2 divided with 10. So this time around, so we have the value of k, so which is ln 2 all over 10. And then using our derived formula, that p is equals to p sub 0 ekt. So we can now have our new formula, that the population at any instant of time is equals to the initial population, multiply it with e, and then k is ln 2 all over 10, or that would make it t ln 2 all over 10. And thus, we have the relation. Okay, so we have the relation of the population at any instant of time, so which is equal to the initial population, and then e raised to t ln 2. It's the relation between the population as well as on the time. And lastly, so we were able to develop our final equation. So we are now on the task of determining, so what is the time? Okay, so when the population is 4 times the initial population. So that is when is the time when the population is 4 times the initial population. So using our equation there, so p is 4 p of 0 is equals to p of 0, then e t ln 2 all over 10. So again, so similar on what we did before, so p sub 0, so it could be taken out from our equation, and thus leaving us the 4, then e t ln 2 all over 10. And taking the logarithm of both sides, so ln e raised to t ln 2 all over 10. And from here, so we'll have ln 4 to be equivalent to t ln 2 all over 10. So we are finding what is t. So that would give us 10 ln 4 is equals to t ln 2, or t then is equals to 10 ln 4 all over ln 2. So let me use a calculator to solve this one. So that is 10 ln 4 and then divide it with ln 2. And that will give me an answer to be equivalent to 20 years. So in short, it would take 20 years in order for the population to quadruple. Okay, so if initially the amount of population is p sub 0 at time is equals to 0, and then it doubles after 10 years, it will quadruple after 20 years. Okay, so that is the first problem is all about. So let's proceed with our next example. So another example states that a population of bacteria grows at a rate proportional to the number of bacteria at any instant of time at the time. So there were initially 200 bacteria, and after 12 hours, the population multiplied by 10. So how many bacteria would there be after 24 hours? So we have another population problem, so which is a growth problem again. So for our given, so we have to identify that initially, okay, so initially, let first that P, so since we're talking about population, so that would be the number. So number of bacteria at any time. And then this time around, so it is specific that initially, so there are 200 bacteria. So initially, when time is 0, so there are 200 bacteria. And then after 12 hours, the population multiplied by 10. So that is after 12 hours. So 12 hours from the initial, so the 200 is multiplied by 10. So 200, so it's multiplied by 10, so that makes it 2,000. So the bacteria accumulates, so after 12 hours. So using this relation, so we are to determine, so how many bacteria would there be after 24 hours. So after 24 hours, so how many bacteria will accumulate? So we can relate this one if you are not brushing your teeth. So let's say initially, so there are 200 bacteria, 12 hours without brushing your teeth. So there are 200 bacteria that would accumulate. So how much more so would accumulate on your mouth if after 24 hours you did not brush your teeth? So let's try to determine. So how many bacteria are present then? So for our solution, so the statement that the population of bacteria grows at a rate proportional to the number of bacteria at any instant of time. So it's just a simple growth problem. Therefore, so we could use our original equation that P is equal to C EKT. So the exponential relation could be used in determining the population at any instant of time. So for our solution, so we will start with our initial value for us to get the value of C. And that is when time is equals to 0. So using this relation, the number of bacteria, the population of bacteria is equals to 200. So from here, so P is 200, and then C, E, K, then the time is 0. So therefore, that would be equal to 1. And then C is equal to 200. So substituting this C to our original equation, so that would give us P is equals to 200 EKT. And then let's use the second statement that after 12 hours, the bacteria increases to 2,000. When time is equal to 12, so the population of the bacteria so increases to 2,000. So substituting those given to our new equation, so that would give us 2,000 is equals to 200 E K times 12. And then dividing both sides by 200, so 2,000 divided with 200, so that would give me 10 is equals to E raised to 12K. So again, we need to find what is K. So take the logarithm of both sides. So ln 10, then we have ln E raised to 12K. So giving us ln 10 to be equal to 12K. And K is equals to ln 10 all over 12. So yielding to a new equation to be equivalent to P is equals to 200 e raised to T ln 10 all over 12. And since we have our final relation between the population and the time, so we can now determine the population of the bacteria so after 24 hours. That is, so when T is equals to 24, so what is P? And from there, so we can now compute the population, and that is by substituting it on our original equation, and that one is when P is equals to 200, then E, the time is 24, so 24 ln 10 all over 12. So using our calculator, so we are going to input, so 200 E, then raised to 24 ln 10 divided with 12. And that will give us, okay, so that would give us an answer, so which is equivalent to 20,000 bacteria. So 20,000 bacteria. So that is, so from 2,000, so it becomes 20,000. So for us, or the bacteria that accumulates, so after 24 hours. Okay, so that is our second example.